Hello everyone, this video is the first video of a 6-part interview with Jean Bricmont. Every video will be broadly speaking, on the subject of the foundations of quantum mechanics. And it will basically be the English version of the series of interview we already did in French with Jean. And for those who still don't know Jean, Jean Bricmont is a professor emeritus of theoretical physics at Louvain University in Belgium, and is the author of several books and articles on the subject, of the foundations of quantum mechanics. Jean has written a very extensive and rather technical book on the subject of the foundations of quantum mechanics. The title is Making Sense of Quantum Mechanics. But if you're not an expert, there is a popularized version of this book, also written by Jean, obviously. And the title is Quantum Sense and Nonsense. And I will put all the links to Jean's book and articles in the description of this video. And for today, this first interview, will be about maybe the most famous issue in the debate of the foundation of quantum mechanics, namely the measurement problem. If you're interested in the foundations of quantum mechanics, I guess you've probably already heard about this issue. But if it's the case, don't go away, because in this interview, Jean will explain to us why, according to him, the measurement problem is in fact not the most fundamental issue for quantum mechanics. The most fundamental issue being, according to Jean, the ontological problem. And the ontological problem is basically just the lack of any physical definition of the wave function. And the wave function is, as you know probably already, the wave function is the most central mathematical object in the quantum theory. So this being said, I now leave the floor to Jean Bricmont. Thank you, Jean, for being with us.
Thank you.
I let you share your screen.
Yes, that's my screen.
Maybe I should say that I called it interview, but I think it will be halfway between interviews and lectures. And as you can see, Jean has some slides.
Okay, thank you very much for the introduction. So the intended audience of this video consists of people who are interested, of course, in the foundations of quantum mechanics and have some knowledge of mathematics and physics, but it's really at a rather low level. It's not aimed mainly at experts. There are a few formulas in the videos, but a layperson could ignore them and still understand a good part of what is being said. The plan of these talks or interviews is as follows. In the first video, we'll introduce the problems of quantum mechanics. In the second video, we'll see why a simple solution of this problem does not work. And moreover, we'll see why certain reasoning based on quantum mechanics show that the world is non-local, which means that there exist instantaneous actions at a distance in nature. This is, of course, a very surprising aspect of quantum mechanics, but it's an important one. The third video will deal with objection and misunderstanding related to the second video. In the fourth video, we'll sketch the de Broglie-Bohm theory, which we regard as a theory solving the problems of quantum mechanics. The fifth video will deal with objection raised against the de Broglie-Bohm theory. And the sixth video will deal with relation between quantum mechanics, philosophy of science, and the broader intellectual culture. The listener who is not interested in every detail may listen to this video, the second one, and the fourth one, and the sixth one is more or less independent of the other ones. It's more broader. To set the stage for a discussion of the conceptual problem raised by quantum mechanics, I'll start by a strange statement due to some of the founders of quantum mechanics another specialist in the foundations of quantum mechanics. First, let's start with Heisenberg, who is probably the first one who has solved the concrete problem of quantum mechanics in 1925. He wrote, the conception of objective reality has thus evaporated into the transparent clarity of mathematics that represent no longer the behavior of particles, but rather our knowledge of this behavior. So the theory doesn't deal with the particles themselves, but with our knowledge of it, which is, I would say, a bit strange. Bohr, according to his assistant Peterson, said there is no quantum world. There is only an abstract physical description. It is wrong to think that the task of physics is to find out how nature is, physics concerned, what we can say about nature. This is the sort of thing which I heard when I was a student, and it really doesn't make much sense because, of course, if you can say things about nature, then, of course, you deal with nature. To say that we are only interested in our knowledge of nature when we never study anything about, perception, neuroscience, or anything that has to do with what we call real processes of knowledge, then it's, of course, a bit strange to say that physics deal with our knowledge of nature and not with nature itself. But Bernard d'Espagna, who is a rather famous French, now he's dead, but famous French scientist, physicist, he said the doctrine that the world is made up of objects whose existence is independent of human consciousness turns out to be in conflict with quantum mechanics and with facts established by experiment. This is very strange because, of course, if the facts are established by experiment, do those facts depend on human consciousness or are they independent of human consciousness? And of course, if the existence of everyday object depend on human consciousness, what was the world made of before there were humans, or before there were laboratories, or before there was life on Earth even? I mean, it seems to me that this is a very, very, very strange proposition. Pascual Jordan, who is one of the founders of quantum mechanics with Heisenberg and Born, he said that if you measure the position of an electron, he said the electron is forced to a decision. We compel it to assume a definite position. Previously, it was in general neither here nor there. It had not yet made its decision for a definite position. And it was the same thing for the measurement of velocities. But it's very strange to do as if the electron has a free will and we force him to take a decision, okay? It's a very strange way to speak. Wheeler, who studied with Bohr and is well known for his contribution to nuclear physics and cosmology, was saying no elementary phenomenon is a phenomenon until it is a registered phenomenon. And he said the past is not really the past until it has been registered. Or put another way, the past has no meaning or existence unless it exists as a record in the present. So it looks like it's very strange because it seems like dinosaurs, for example, have not existed in the past until we discovered their bones or something like that. I mean, it's a sentence which I really find very hard to understand. And the best one is probably one by David Mermin, who is a professor, probably retired now, of Cornell University, who is well known and has worked a lot on foundation of quantum mechanics, and say we now know that the moon is demonstrably not there when nobody looks. And this sentence refers to a conversation between Abraham Pais and Einstein when Einstein was at the Institute for Advanced Study in Princeton, and they were together walking back to Einstein's home, and Einstein was extremely upset and hostile to this talk about, we are always talking about our knowledge of things and we're not talking about the world and so on and so forth. And then he said to Pais, do you really believe that the moon is not there when nobody looks? And Mermin says, this was for Einstein a reduction ad absurdum of the ordinary doctrine. And Mermin said, no, the moon is really not there when nobody looks, which to me makes no sense at all. But where do these ideas come from? Well, I will start by explaining it. Consider the double slit experiment, which Feynman, which is one of the greatest physicists of the 20th century, says this contains all the mystery of quantum mechanics. Not all the mystery of quantum mechanics, but it's something, it explains, it illustrates a lot of the problems. So you have a wall here with two slits, and you are a source here sending electrons or photons, let's say electrons, and you have a wall here which records the impact of the electron. So if you have you close one slit or one hole and you have the other one open, then the particle will have a certain distribution. They will not all end up at the same place because they don't have all the same velocities or position, and you may have a curve like this. Of course, if you close this hole and open this one, then of course you get a symmetrical curve. But the mystery happens when you open both holes, because then you would expect to have the dotted line here as a result, which would be just the sum of these two lines. But in reality, you get these wavy lines. And then you notice that there are places like here where there are no electrons coming, where there would be electrons coming if only one hole was open. So you get the impression that if you open the other hole, then it makes electrons that would otherwise have reached this point, it makes it impossible to reach it. And that is, of course, the very strange behavior. And of course, that behavior is characteristic of waves, because if you send, instead of particles, you are sending waves, then the waves would there would be two waves coming from each hole, and they would interfere with each other. And this wavy behavior is something which you would actually expect. But of course, you would not detect a wave at one point. You would have a spread out wave, like a water wave or sound wave, etc. The paradox is that you always detect particles at a single point, okay? And that's sometimes called the wave-particle duality. And there's a lot of loose talk about the electron behaving like a particle if one hole is open, like a wave if both holes are open, etc., which is very mysterious, because the electron, of course, doesn't know how to behave before he reaches the first wall.
So the wave-particle duality is that in one hand we have an interference pattern on the second wall, and this pattern is the result of the collective behavior of, say, electrons, for example. But for each position measurement, we always find each electron in a single place. And so we have
it behaves like a particle. The collective behavior is like a wave, but the individual behavior is the one of particles. By the way, I should stress that in this experiment, you send electrons one by one, so there is no question about interaction between electrons. This is just, at least, you know, that's what it's supposed to be. And here there is another picture which is similar, but it gives you the recipe how to compute those curves. You associate to each hole a wave, which has a certain intensity, and the probability of finding the electron here, if only one hole is open, is the absolute value of phi1 square. And the other curve is the absolute value of phi2 square, where phi2 is a wave associated with this hole. And if both holes are open, then you have to do the sum phi1 plus phi2, and that square, and that gives you that wavy curve. Because if you take the square, if you take a plus b square, then it's a square plus b square, so you get phi1 square plus phi2 square, plus 2 phi1 phi2, and moreover, they are complex numbers, but left that aside, I mean, you get the double product, and that, of course, modifies the curves. You don't get just the sum of these two curves. And that's the recipe. That's the recipe. Okay, here I illustrate the recipe with pictures. Here you have a propagation of a wave, which would end up like this. If one hole is open, that's what the other hole is open, and that's a picture when both holes are open, and there you see interference pattern, and then you see that there are places where the wave cooperate, and then you get this picture, and there are places where they interfere negatively, and then you get this picture. And this is just mathematically perfectly clear, but the mystery is, why do we detect always particles at one place? Okay, now this waves is called a wave function. And the rest of this lecture or talk or the interview will be about what is a wave function. The way you see it in elementary courses is something like this. You describe electrons around the nucleus like this. You have here around, and then you have this picture and this picture and this picture, etc. You get all these different pictures. What they mean is they are the regions where the wave function is appreciably, is really different from zero. where it's the support, if you wish, of the wave function. It's not really strictly the mathematical notion because the wave function extends to infinity, but let's say the region where it's sufficiently different from zero. And so these are different wave function, okay? These different pictures. But then, of course, what is the electron? What is the position of the electron relative to these pictures? This is the picture of the wave function. And then you can say, well, they give the density, the probability density of the electron being somewhere, or the probability density of the electron being found if we measure it. You can also think that maybe it's a cloud. You know, there is no particle, there is a cloud or something like that. And then when you measure the electron, then it condenses at one point. I mean, these pictures are in every chemistry book and maybe even in high school, etc., but their status is not very clear. So let me go to a more precise mathematical definition. For a single particle at a given time, the wave function is a function, just a function. X, Y, Z are coordinates in R3, okay, and psi is a function. And that's defined in ordinary space, and it makes sense to speak of its value at a given point. And the orbitals, these are called orbitals, they represent regions where the wave function is significantly different from zero. To explain the first problem raised by quantum mechanics, namely the so-called measurement problem in simple terms, let us consider other quantities than the position of the electron that can be measured, like the velocity, or the momentum, if you wish, the energy, the angular momentum, and so on. Given a wave function at a fixed time, and a physical quantity can take different values, A1, A2, An, usually I will consider quantities that take a finite or discrete set of values. There could be even a continuum set of values, but it's easier to take this example. Then there is a quantum algorithm that will be described at the end of this video, but I won't give it now, that calculates the probability to obtain one of those results. For simplicity's sake, as I say, we consider a finite number of possible values, but it could be infinite and even take a continuum of value as for the position or the velocity, okay? And the problem is the quantum algorithm associates to each of these possible values a function, with a function, psi1, psi2, psi-n, and after a measurement, you obtain the result A1, then the wave function, which used to be psi, suddenly becomes psi1. If you observe psi A2, then it becomes psi2, etc., etc. These jumps, because this is a jump, the discontinuous behavior of the function, they are instantaneous and random. They are random because they are governed by these probabilities. We can't predict what will happen. And they are incompatible with the evolution of the wave function outside of measurements. Indeed, outside of measurement, the wave function, which I mentioned here, it evolves in time. I've not indicated the time factor here, according to Schrödinger equation, which I'm not going to write down, but it's an equation, a partial differential equation, which tells you how the wave function evolves, and it evolves continuously, smoothly, and you know, and it's deterministic. So if you give the wave function at a given time, then the Schrödinger equation tells you what the wave function will be at a later time in the absence of measurement. If there are measurements, then you have the jumps.
So we have two
yes.
dynamical rules, one for the time evolution of the wave function between measurements, and one during measurement, which is the collapse postulate. And
collapse postulate, yes.
And whatever the wave function was before the measurement, if we find, say, A2 as a result of our measurement, we say after the measurement that the psi function, the wave function, is now psi2.
Exactly.
Okay, and so it's how can I say that? It's a sudden. I don't know if sudden is the right word. It's a leap. It's like a quantum leap.
If you wish, yeah, it's a jump.
A jump, yes.
And if you take the double slit experiment, you can think of the wave function propagates continuously. That's these wave function phi1 and phi2, they propagate continuously, but it condenses itself at a point when the particle is detected on second wall. Maybe a point is mathematical idealization, but it certainly condenses itself at a, you know, it becomes localized.
Yes.
And so the measurement problem, the way it's usually solved, is to understand how those jumps are possible, because they contradict the basic evolution of the Schrödinger equation. Of course, the point is that, but I think there is a more basic problem, and that's what you call ontology. I don't like that word, but I will use it. Because the problem is that quantum mechanics predicts with great precision, the probabilities of results of measurements done in laboratories, but does not seem to say anything else, in particular, nothing about what happens outside of laboratories. And it is because measurements play a central role in the quantum formalism, I mean, in the real definition of the theory, and because measurements are not defined independently of the formalism, that people make the bizarre statement mentioned at the beginning of this talk. Because then these measurements are really, of course, done in laboratories. The laboratories are done by human beings, etc. And therefore, people say, oh, it's all due to observation, it's all due to us. We are talking about our knowledge, which is our knowledge are the result of measurements. We're not talking about the nature, etc., because indeed the formalism speaks only about what happens in laboratories, and that's the basic problem. This problem is linked to the famous one, which is Schrödinger's cat. That cat, I mean, Schrödinger imagine the following situation where you have a quantum radiative decay or something like that, some quantum effect that can either happen or not happen. And if it happens, it triggers a hammer that breaks a bottle in which there is a poison. And there's a cat in the room, and if the poison is if it's released, the bottle is broken, then the cat dies, and if not, it's alive. So what it takes this whole situation, and since the particle here is both, the quantum event can either happen or not happen, it's in a superposition, the wave function is superposition of being the event or the disintegration, if you wish, occurred, and the disintegration did not occur. And then, as far as the cat is concerned, the quantum state or the wave function becomes a superposition of cat alive plus cat dead, and it jumps into one of those two terms when we look at the state of the cat. And of course, Schrödinger called it, in German, he called it burlesque, and it's usually translated ridiculous in English. I mean, Schrödinger, of course, thought it was a reduction ad absurdum of the usual quantum formalism, okay? But many people nowadays seem to think that the poor cat is both alive and dead before anyone looks at it, which is an expression which I really don't know what it means, and there is no argument to justify that view, and was certainly not what Schrödinger thought. I mean, you just read Schrödinger and see that it's not what he thought. The wave function of the cat, or the quantum state, to be more precise, is a mathematical object, which is not to be confused with a real cat. You see, even the cat alive or the cat dead is a mathematical object. The cat itself is an object in 3 dimensions. It's a familiar object, but it's not a mathematical abstract object as it is. And this problem is linked to the problem of meaning of the wave function for more than one particle. Because for 2 particles, the wave function is of the form psi of x1, y1, z1, x2, y2, z2, where x1, y1, etc. are coordinated in R3, each triple being associated to one of the 2 particles. Thus, the function is not a simple function like a product of a function of those variables times a product of function of those variables, or a sum of such function. No, it can be a complicated function, and that's what is called entanglement. We'll come back to that in the next video. This wave function is defined on R6, and this function cannot be viewed as a function defined on ordinary space, unlike the atomic orbitals.
So this function has no definite value at any specific point in the 3-dimensional space.
No, of course, because it's defined on R6.
No, yes, I just wanted to
if I give you these 3 coordinates, for example, that would be a point, but I don't give you those coordinates, then you don't know what the value of psi is.
Yes.
For n particles, the wave function is of the form, it's the same thing, but it's simply more complicated. You have a triple of coordinates for each of the particle, and then the wave function is defined on R to the power 3n. That's a vector space of 3n dimension, and n could be Avogadro's number. So this function cannot be viewed as a function defined on ordinary space. Thus, its physical meaning must be totally different from the one of ordinary wave, like sound or light wave. Because if you take a sound wave, a electromagnetic wave, etc., all these waves are always defined. Even for if you have many electric particles, for example, they generate an electric field, but the electric field is defined always on R3, even if it's the one generated by several particles.
So the main difference is that if we take, for example, the magnetic field, we can say what is the intensity of the magnetic field in any specific point in space, and it's just impossible to do the same thing with the wave function of a many particle system.
Exactly. And so the wave function of the cat, since the cat is composed of many particles, doesn't have a clear physical meaning. As I say, for a single particle, that quantity, which we have encountered before when we discussed the orbitals, for example, can be interpreted as a density defined on ordinary space, and could be either the probability density of the presence of the particle or the probability density of finding the particle somewhere if one bothers to measure its position. But for n particle, the function cannot be interpreted in such a way. In particular, the wave function of the cat, whether that of the living cat or the dead cat, cannot be identified with a cat, which is an object localized in ordinary space. And the fundamental problem of quantum mechanics, even more fundamental than the measurement problem, is to understand what the wave function means outside of laboratories. But before proposing a solution to this problem, we need to tackle another mystery of quantum mechanics, which is the non-locality of quantum mechanics, and that will be for the next talk. However, I will end with a bonus for the mathematically inclined listener. I will just give you mathematically the quantum algorithm. The wave function psi is a unit element of a vector space, technically a Hilbert space. And measurable quantities like the velocity, the energy, the angular momentum, etc., are represented by self-adjoint operators acting on that space. The easiest example, and we'll encounter such example later, consists of self-adjoint matrices acting on a finite dimensional vector space. And let A be such an operator or matrix. Since it is self-adjoint, it has a basis of eigenvector. Can be, putting aside the fact that they can be generalized eigenvectors and they can be degeneracy, etc. So I write the eigenvectors like this: A psi I equal AI psi I, where I goes from 1 to n, where n possibly can be infinite. And the AIs are the eigenvalue and the psi I the eigenvector. The eigenvalue AI are the possible values that one obtains if one measures A. That's what I was describing before in the lecture. And if you obtain the value AI, the state jump from psi to psi I being the vectors I was describing in the talk earlier. And if you are interested in the probability of obtaining the value AI, you have to write psi in the basis of eigenvector, because this it has the operator has a basis of eigenvector, and they form a basis, and the probability of obtaining value AI equal the coefficient of psi I in this decomposition, absolute value square, Ci square. And that's just the algorithm for those who are interested.
Okay, so if I try to summarize your talk, the measurement problem is a dynamical problem because there are two different rules, one for measurement, one outside of measurement, and we can illustrate this the measurement problem with the Schrödinger cat, because if the claim is like many people still do, that the cat is live and dead in the end of the experiment, or before before we observe the cat, the measurement play a central role. I don't know role, but
yes.
And the state of the cat collapse because of the observation of the
collapse.
But there is a different issue, which is, according to you, the most fundamental one, and this is the fact that the cat's wave function is not the cat, and the cat's wave function hasn't any clear physical meaning in the quantum theory.
Yeah.
Correct, or?
Yes. Well, the point is that, of course, the two problems are related, if you wish. People focus on the measurement problem, but the problem is really that the way the theory deals only with measurements, it doesn't deal with the world. And that's why we have all these strange claims that we made at the beginning, which I don't think are correct. I don't think they are warranted, but they are motivated by the fact that the ordinary quantum mechanics does not give a clear meaning. If I take an electron out here and I give you its wave function, I say, what does it mean? You have to tell me, all you can say is that if you take the electron, bring it in the laboratory, and then make a certain experiment, then you'll get such and such result with such and such probability, which is given by this algorithm. But the electron out there, the wave function of the electron out there, I'm not sure what it means.
Okay, so there is this measurement problem because of the ontological problem.
In a sense, you could say it like that. Well, you could say it like that, yes. I mean, people usually focus on the measurement problem because there are these two rules of evolution. But I think the problem is deeper. Indeed, the problem is really, I don't like the word ontology because many physicists are afraid by this word. I would rather call it the meaning problem, the problem of what does the wave function mean? What's the physical meaning of it? You see, in classical mechanics, you can speak of the motion of the planets, and it's perfectly clear what the motion of a planet means. And to some extent, it's also true of electromagnetic fields. They propagate in space. You can imagine that. You can imagine propagation of waves and so on. But once you go to quantum mechanics, it's not at all clear what it means, except, of course, as I say, in the laboratory. Okay? So.
Okay.
So.
Thank you very much, Jean.
Thank you.
And see you soon for the next interview.
Okay.